Yeah, thanks for the very kind introduction. So the title of today's talk, as you can see, is The Era of Quantum Computing is Here, but I was not so sure if I really can use that because it's also near. And in my talk, you'll see why that is. So it is because some of the things or the devices that we have out today, we can use them for some of the things that we're working on and solve some real-world problems, but we expect a lot more in the near future. And so this is why some of it we have today and some of it is still to come. And the talk today is divided into two parts. So the first part will be a little quantum theory and how to use this for computation. And the second part is practical examples, so the things we have been working on. And I always have an easier time understanding something when I talk in examples. So I can't understand anything without a picture. So that's why we hopefully can discuss these examples and after the talk, have some time to answer questions as well. Yeah, as announced, let's start with the boring part. And quantum theory is everywhere. So we use it in, for example, lasers. So you know lasers, when you emit an electromagnetic beam, so you have photons with the same wavelengths and the same energy. So this was crucial to understand quantum theory to develop lasers. Without it, it's not possible. We use it in medical devices. So for example, when we have nanoparticles that exhibit some quantum effects and we attach them to disease-fighting cells and we can make them visible in magnetic resonance imagery. So there we have quantum theory. So we see quantum theory here in the evolution of the universe. So this very nice and beautiful picture shows Laniakea, which is our local supercluster, so the cluster of galaxies where you can also find Milky Way. And it has about 100,000 galaxies and spans 160 megaparsecs or 520 million light years. But quantum theory governs this evolution. So in about 13.7 billion years ago, our universe was super small. Actually, it was 1 billion trillionth of centimeter, which is Planck size. And this is where quantum effects are relevant. So you see, it's also on a very big scale. Where we start small, we can see quantum theory applied. And of course, we see it in material science. So when you want to simulate electronic structure of molecules, you want to learn about materials, you want to find some better materials for batteries, cathodes and anodes, for example. And we use it for computation, so some of the effects. So some we haven't really completely understood, but that doesn't matter. So as computer scientists, we can still understand them enough to use them for computation and achieve something useful. But what does this mean in more detail? So, you know, we have four forces out there that we know. We have the electromagnetic force, like light. We have the weak interaction, which is in some forms of radioactive decay. We have a strong interaction, which holds together the atomic nuclei. And we have gravity. And three of these forces, the first three in this slides actually, we have united them with quantum theory. So, and for uniting gravity with quantum theory, so this is a big part in physics and active research, and no one has really found a solution to that now. But so you could see these three forces as higher level languages. So, and quantum theory is the machine language of the universe, and all the other languages sit on top of it. So, and this is where we start with computation, actually. So usually in physics, we don't call them higher level languages, so we have nice and fancy names like quantum electrodynamics or quantum chromodynamics. But also when we come to computation, what are the initial, or how do we start actually? So the initial configuration of a system is, for example, fields and particles and such, and we evolve this system over time. And we will learn about two architectures that are out there, quantum annealing and universal gate model quantum computers. And they're slightly different in how you evolve over time. So the first system starts with initial energy configuration and you introduce your problem, Hamiltonian. We'll learn about the Hamiltonian later. And the other one is stacking together a sequence of gates. So you try to solve a problem that way. So like you know, in classical computer science, you have, so anytime, by the way, I say classical, I mean non-quantum. So classical computer is like the laptops we use and the servers. And quantum computer is the quantum computer we talk about. Classical physics and quantum physics. So that's the distinction. You see, when you all know Moore's law. So basically what it says is that approximately every 2 years, you double the number of transistors on silicon chips, so which means you have a lot of more power. But if you extrapolate this up until, let's say, 2050 or so, what you would have is very, very small computers, atomic size, molecular size. And while it's possible to engineer such computers, it's very inconvenient to handle them. So if you don't want computers that are difficult to handle and get really, really hot, we need to find something else to use for computation. And this is quantum effects, so exhibit quantum effects or use quantum effects for computation. So for certain problems, we already see today that they're millions of times faster than classical computers. So and the question that we must ask ourselves is, of course, are these problems that are useful? So we'll also see later on that there's this distinction between these problems we talk about in academia, where we try to experiment and show that a quantum computer can do something that a classical computer will never be able to do. But is it useful? So most certainly not. So what we really want is to use these computers for something that makes the lives easier for society, that improves something for our customers, make our products better. So many institutions so not only Volkswagen, but like Google, Rigetti, D-Wave, these are quantum computing companies, they invest millions of dollars in research. And there's also this big flagship initiative in Europe that's going on, so where there's 1 billion euros in quantum technologies, which is not only quantum computing, but also quantum sensing and a lot more. Anyway, so let's talk about the computation. So, and there are 3 quantum effects that I want to mention here that are very important for what we can do with quantum computers. And the first one is superposition. So we know that in classical computer science, the smallest unit of information is the bit. And 1 bit can take a value of 0 or 1. And as long as I don't know, let's say I can look at this bit and apply some transformations and know all the time what's happening to this bit if I wanna have that. But then when we come to quantum bits, so which is the equivalent in quantum computation, then it's different. So we have bits that can take a superposition of values. So let's say I again have states. So we talk about states now. States 0 and state 1, as long as I don't look at it, and looking at it, depending on the implementation of a quantum bit, could be interacting with polarized laser light or magnetic fields. As long as I don't look at it, it takes both values at once, so 0 and 1 at once. And imagine if I have 2 quantum bits, which can take 2 states, I have 2 to the power of 2 configurations this system can take at one time, as long as I don't look at it. If I have 3 qubits, I have 2 to the power of 3 equals 8 configurations. And if we more practically think about problems, what does that mean? So imagine I have a problem and 10 different solutions that I want to check. And I want to find the best solution to this problem. With a classical computer, what you can do is evaluate all problems or all solutions in sequence. You can, of course, split in 2 times 5 and evaluate in sequence, so parallelization, but it's still evaluation in sequence. But with a quantum computer, as the system takes all the solutions at once, I can evaluate in one step all the 10 solutions and find the best one, so, which is very powerful, as you can see. And so the other thing that's worth mentioning here is that in computer science, we haven't had this remarkable harmony with physics. So whereas with mathematics and physics, we always had it. So, and quantum bits, I'll tell you about. So why this is, quantum bits are slightly different. So imagine you use an electron for a quantum bit, for representing a quantum bit. An electron has 2 spin values, spin up and spin down. So this could be your quantum bit. Most of the quantum bits today are actually superconducting qubits, which are implemented on superconductors. It's metal rings like niobium or aluminium. And you cool them down to about 15 to 20 millikelvin, which is close to the absolute zero. And you know when you cool down superconducting metal, then you don't have resistance anymore. So you can induce current in both directions. And what you get is, as it's electromagnetic movement, you get a magnetic field up and a magnetic field down. So for each direction of the current, you get 2 fields. And this is your quantum bit. It has up and down, -1 and 1. So this is what you can use for computation. The second effect that's of utmost importance is entanglement. So it's not 100% understood what entanglement exactly is, but that doesn't matter. We use it for computation anyway. And what this means is, imagine you have 1 qubit, so 1 bit here. What it means for us as computer scientists is if I do something to that qubit, it can affect what's happening here to another qubit, or 10, or 100, or 1,000. And the very interesting aspect of this is, so this doesn't really matter for quantum computing, but there is no time delay. So the communication, if you can say it's communication, is instantaneously. So if I had one qubit here and entangle it with one quantum bit in Andromeda galaxy, still there's no time delay. If I do something to that qubit, it happens immediately. So how can this be? Because this would violate special relativity. Nothing can move faster than light. But we just say there is no communication, so and it's solved. So anyway, we use this for computation. And this is very important because you cannot, combined with superposition, you can not only evaluate all the possible configurations of single bit states, but connected bit states. So all the possible interaction between electrons when I simulate materials, for example, can be evaluated at once. So this is the second effect that's responsible for the remarkable power of quantum computers. And the third effect that we need to mention is quantum tunneling. And this is only relevant for quantum annealing systems. So these are the first system. We'll learn more about that later. Imagine you have a particle flying through space and you have an energy barrier. So in the classical world, non-quantum, what would happen is if the particle approaches here, this barrier, it wouldn't be able to pass through. But in a quantum world, it can. It can just tunnel through. So, and this is something that's very important if we are looking for minimum value solutions and you have a valley here and maybe the deeper valley is here and I want to find that valley. So I need to fly through that barrier and end up in the deepest valley so I find the best solution. Whereas a classical algorithm maybe would get stuck in the other valley and not the deepest valley. So, and before we go on, we need to think about, so nice to have these quantum effects, but why is that important? So the thing is that most of the world's most important problems will never be solved with classical computers. And this could be problems in transportation and logistics. So we have some examples on that, and I'll not go into detail here now. But even more important is simulated physics or simulated chemistry. So simulated chemistry when we want to find new drugs. So you have interactions between atoms and the electron interaction is again the important thing. So you want to find the best drug for a certain disease. So we will find drugs that can heal diseases that can't be healed today. Same for material science. What you can do is simulate materials exactly. Right now, what we can do is only to a certain degree, to a certain size of the molecule, which means the number of electrons, approximate. So an approximation is nice to have, but it's never as good as an exact simulation. So it doesn't give me the full understanding of the material. We have it in artificial intelligence and neuroscience. So in artificial intelligence, it's important because you know most of the latest machine learning algorithms, such as deep networks, so it's very performance intensive to train such networks. But what if I could take the weights or the weight space, all possible weights that a neural network can take and map this on a quantum chip and in superposition find the best configuration at once? Or maybe create an iterative algorithm that does that a lot faster than classical training algorithms. And in neuroscience, so we don't even know today if, so I told you before that quantum effects govern the evolution of the universe, but if it governs the evolution of the universe, does it also govern conscious perception? So we don't know if quantum effects play a role in our brain chemistry or how our brains work and how we consciously perceive things. So now let's talk about the two different architectures of quantum computing. So the first one is quantum annealing. And quantum annealing systems are suitable for solving two kinds of problems. So, and one is optimization, the other is sampling tasks. And the machine learning engineers among you will now say, well, that's perfectly suitable for what I do. And sometimes it is, sometimes it's not. So it always depends on the problem size. What these systems do is imagine you have a classical, or let's say you have a problem. And you represent this problem as a surface. So you find good solutions on top of the hills and bad solutions in the valleys. And what a classical algorithm can do is start somewhere and walk this valley. You can parallelize again and set 1,000 points and walk down and maybe get to a deep valley. And if you set certain parameters right, you can maybe jump over that hill and find a deeper valley. But in the worst case, what you will end up with is not the optimal solution. So it will tell you this is the best thing I can find, converged, but it's not the best thing that it could do. So, but with quantum annealing systems, it's different. So before we learned that you have this particle that just flies through the energy barrier, and here it's the same. This particle starts somewhere, and what it does is fly through all the valleys and hills and end up in the deepest valley, and so find the best solution. And it does that remarkably fast, so it takes only microseconds to do that. So if you can fit your problem on a chip, and if it's a problem that can be solved in 1 iteration, you have the solution to your problem with communication time to the machine, let's say in 1 or 2 seconds, compared to classical algorithms, maybe that take 1 day. So we have these other comparisons. I'll talk later about that, not too much detail now. So and the corresponding classical optimization problem is the one that you find here on the bottom. It's, if you want to look it up, it's called quadratic unconstrained binary optimization. And no, there is no laser pointer, but you see the first term here, the AIQI. So what this does is it influences the value of the output of 1 qubit. Q stands for the qubits. And the second one, what you have here is this BIJs, is the interaction between the qubits. So any quantum chip that we see today is implemented as a graph, so an undirected weighted graph. And what this means is that you have nodes, your qubits, connected to other nodes, and you have connections that are weights. So if you look at that, that looks remarkably similar to a neural network. So a very natural idea is actually to fit a neural network directly on the chip and see if I can gain some advantage. This is also something we did, and we'll talk about it in a bit. So, and you can use it for sampling. So you can assume some random distribution, and as these systems will always end up in the minimum configuration, if you can represent your problem as a minimum energy problem, let's say I want to find the optimal configuration of weights in a neural network, then this is a minimum problem. Then I can also use these systems to just sample the weight space and hopefully end up with better weight configurations. And then the second kind of systems that we have is gate model computers. So sometimes you hear gate model computers, sometimes you hear universal quantum computers. And you say universal because in theory you can implement any arbitrarily complex algorithm as a sequence of gates, 1 qubit gates, 2 qubit gates, n qubit gates. And we'll have an example on the next page, but I think that helps. What you can see here is a circuit diagram. So this is usually how you draw your algorithm. So you have this sequence of gates, like this H gate here. This example here represents the Hadamard transformation. So and this Hadamard transformation does what we talked about before. You remember when we said 1 quantum bit can be in a superposition, so an equally weighted superposition of 0 and 1. This is what the Hadamard gate does to this state. So you use an input register given by psi in that case, you apply the Hadamard transformation to it, and it's in superposition, and then you do something with it. So anytime you see this measurement icon here, it refers to measurement. So this is also a very important point that I haven't mentioned yet. In the end, so once you calculate, or once you did all these, or applied all these gates to your input states, you measure this system. So and before you measure it, it exists in this rich superposition. So it has information about all the possible solutions that it can take. But once you measure the system, it collapses. It collapses to exactly 1 solution. And here in universal quantum computers, the whole artistry is to make all the other solutions before I measure the system very unlikely when I measure it. So you can imagine solutions as arrays in space. It's a complex vector space, so you say arrays in Hilbert space. But imagine you have an equally distributed set of rays. So they have the bad rays, the solutions that don't give me the good solution, and you want to move them to almost impossibility when you measure the system. And the good ones, so you want to give them a high probability. But remember that a quantum system will always be a probabilistic system. So even if you have a good algorithm, you may end up with a bad solution. So therefore, you don't do it once. You calculate it 1,000 times, 2,000 times. And 800 solutions of your 1,000 solutions may be identical or similar. Then you know this is the solution I want to find. And 200 are some random. I don't want these, so leave them away. So that's also very important to understand. Yeah? And we had this before. So one very important definition is the useful quantum supremacy. So very often you'll hear hardware vendors talking about quantum supremacy. So this one experiment that can show that you can do something with a quantum computer that no classical computer will ever be able to do. But the first thing you need to ask is it useful, or what exactly is it? So when we talk about quantum supremacy, we mean something like simulating materials and really finding new battery materials, for example. That's very useful. So if we get to that point, that's still a very different story to compare what we understand in academia under quantum supremacy. Both is very important, but for the one that we're interested in as a company, you need more quantum bits, you need better error correction, so you need bigger systems. And this may take a while from now. So, and as we have these small systems today, it's not possible, or very often you don't have pure quantum algorithms. Also, what you don't use most of the time is quantum data. So you can distinguish between classical and quantum data, and a classical chip and a quantum chip. So let's say we want to do traffic flow optimization. We want to maximize the traffic flow for vehicles in a traffic graph or in a city. Then you have classical data. Moving vehicles is certainly not quantum data. But if you solve the optimization problem on a quantum chip, then you have a quantum solution to that. If you have material simulation, so you want to simulate electrons, then you want to simulate quantum behavior, so you have quantum data. And you use a quantum chip, therefore you would find it here as a QQ. So this is just a distinction, and we didn't come up with that, some other people did, but it's very useful to understand where we are today. So most of the algorithms that we develop and come up with are quantum assisted, so it's not purely quantum. And so now I want to talk about some examples, because as I said, I think this is most useful in understanding what we can do with these systems. So and here is just a summary of what we did so far, but one of the problems we've been working on is, so to your left side, is finite elements design optimization. So it takes a very long time if you want to, let's say you have an outside mirror of a vehicle, and you want to minimize the wind noise where a passenger sits. So how do you find the optimal design that must still resemble a mirror but minimizes the wind noise? So wind noise actually, or the noise where the passenger is vibration caused by wind noise. So it's a sound pressure that's emitted by the mirror. And so still we solved a simplified problem. So what we did here was we started with a sphere and developed an algorithm that still keeps the shape of the sphere, but it reflects or deflects all the rays that usually would hit these rectangle in the back. The rectangle is the area in which the user moves. Another thing that doesn't work right now, anyway, was traffic flow optimization. So we want to find the optimal configuration or distribution of vehicles in an ideal scenario, not have traffic jam at all. This was what we did with D-wave machines, so, or quantum annealing systems. So, and what we do with gate model systems, so here material simulation is most interesting as well. So we can do material simulation with the quantum annealing systems that we had before, but it's not optimal, so, and doesn't scale well. So what we really want is use gate model computers for doing material simulation, and of course optimization. So let's talk about this in detail. So what we did was take each vehicle of this traffic graph and imagine you have some software that helps you find the optimal route. So it analyzes real-time traffic. So you would go on a road and would tell you where here's traffic jam. So you should go to the right, and 300 vehicles move to the right and cause traffic jam there. So this is not an ideal solution to that problem. What you really want to do is have an algorithm that predicts where traffic jam may happen in 15, 20 minutes, and then take these vehicles that contribute to the traffic jam and redistribute them such that no traffic jam is caused at all. So here we see an example for a classical or quantum classical algorithm. So we have this classical prediction, classical machine learning algorithm that tells us where traffic jam is going to happen. And then we redistribute the number or all the vehicles that contribute to the traffic jam under consideration of all the other vehicles around them such that no traffic jam occurs at all. And you can see this is a very complex problem. So because if I have, let's say, 500 vehicles and if I have 3 routes that I can potentially assign to each of these vehicles, my solution space is 3 to the power of 500, which is fairly big. So, and with a classical system, to find the optimal solution to that, it may take hours or a day. So in some algorithms we used, or we ran up to a day and didn't find the same solutions that we could find with a quantum chip. So and with a quantum chip, it takes us about 3 to 4 seconds in that problem. And it's important to say it doesn't solve all the traffic problems in the world right now. It's an abstraction. So we don't consider different speed limits at the current point. We don't have interaction with infrastructure, so we don't communicate to traffic lights. So there's a lot more to do. But still, what we wanted to show is that it works. And yeah, maybe we can, in the future, optimize optimize the routes for charging pillars as well. And this is a problem that's perfectly suitable because we collect information, so position data from vehicles every 1 to 5 seconds. So it's not possible that I wait 10 minutes, 15 minutes to get a solution to a redistribution, because if I do that, the vehicles are on totally different positions, and it doesn't help anymore. So it doesn't help at all. So I want to find the best solution as quick as possible. Another thing that we have been looking into was quantum-assisted reinforcement learning. So, you know, reinforcement learning is when you give an agent the ability to move in an environment and so either move physically or simulate movement in an environment and learn by interaction. So let's say you have a robot that's learning to walk, or you have some other robot that's trying to find the shortest route from A to B in a room filled with obstacles. So, or you have parking maneuvers. So let's say I want to teach my vehicle to reverse park. So one way to do it would be you have a driver doing that 1 million times, and you record everything that happens, and so learn the vehicle how it does that. But better, you do it with reinforcement learning. And ideally, what you want to have is vehicles that are equipped with reinforcement learning algorithms and do that all the time. So it's not that we always want to train systems and only deploy trained systems. So we really want to give the vehicle the ability to learn by simulated interaction. So assuming, a very simple example, but assume you have a vehicle entering an intersection, and the target is on the left side, or the goal, so where it wants to go. But then suddenly, all of a sudden, there is a truck standing around. So what to do? You can't just stop because it would block the traffic behind you. So ideally, it would simulate what's the best thing and go around that block and find its way to the target differently. So, and the problem here is that the more steps to the future I want to simulate and the more action I have to my avail, the more complex and time-consuming this problem becomes. So what I really want to do is find these solutions as fast as possible. And we could show that by mapping observations on the chip, we can again find them in some seconds. So the optimal configuration. Or clustering. So, you know, we talked about the architectures of these chips. So imagine that a chip with its nodes and all its connections, you just take it as it is and randomly initialize everything, and then you feed in instances. So, and what you want to do is find unknown behavior. So you know which areas on the chip light up when you feed in certain instances, and hopefully similar instances will have similar areas on the chip fire. Fire means qubit outputs of 1, and not fire means qubit output of -1 or 0, depending on how you interpret it. So, and if you can do that really fast, that can be very valuable for threat detection in IT networks. So you want to see or find unknown behavior as quick as possible. And if it's a threat or not, you can solve that manually or feed it into other algorithms. But in the first instance, if I can be seconds or minutes faster than my existing systems, that's very valuable already. And neural networks. So what you see here is a very simple feed-forward neural network, so which is a weight matrix. So, and again, it resembles a lot the architecture of these chips. So you can represent different sets or configurations for one weight in a superposition between 2 qubits. So the coupling terms or your graph can again be in a superposition of all the weights you want to feed in. So, and right now we feed in 10, 20, 30 different weight configurations, get the best out of it, and then feed it in again. So, but still we're faster. And we can map one neural network multiple times on a chip depending on the size. So let's imagine you have a small neural network and you have all of these weights of the neural network in superposition, and you have this neural network mapped 20 times on your chip. So again, you have a way to find optimal configurations a lot faster. But very important to mention, we are still at the beginning. So D-Wave systems right now have 2,048 qubits, and each qubit is connected to other qubits with so 6 coupling terms. If you need 10, you need to you do chaining, which is just duplicate the input values. So you see, you're limited by the size of the chip. And what we expect is with growing hardware, solve more complex problems. And we know there's something going on, so very soon we'll see some improvements in these chips as well. Yeah, that was just what I explained. So when you feed in a problem to a D-Wave system with all these weights and interactions, what you do is just create a big matrix. So you feed in this matrix, which is given by Q here, and what we minimize is different configurations of weights. And we have Y hat, which is our prediction. So I know the difference between what I want and the difference between what I want and what I get. So this is again minimizing the error, so a minimization problem, very suitable for such systems. Another thing that's very important is simulation of electronic structure. So, and you know, when you have molecules, they consist of a number of atoms. So you have different nuclei that interact with each other. You have electrons around these nuclei that interact with other electrons in that atom. You have electrons interacting with the electrons of the other atom, and you don't have only two. So, and one example is a caffeine molecule. So caffeine molecule is, so the electronic structure of a caffeine molecule is something that you will never be able to simulate on a classical computer. It's just too big. So, but with a quantum system, so let's say we have an optimal universal gate model computer, it is assumed that we can do it with 160 quantum bits, which doesn't sound a lot. Right now we have 72. Actually, we don't have it, Google have it. So, but we work with these systems. So, and yeah, so we see some advantages here as well. As we are running out of time, I think I'll skip that quickly. So this is so one example how a solution looks on a chip. So you can always extract the graph from a chip, and you see these 6 connections from each quantum bit to other quantum bits. And here, the solution legend gives you the output of the value of the values that the qubits take. So what you get as a result is a vector with -1s and 1s. So and the -1s are the off qubits. The ones are the on qubits. And ideally, you create a reference when you submit your problem from qubit ID such and such, and finally you can conclude back from this value 1 is qubit such and such, which means this configuration of the weight. Whatever. So this is how it works. Some examples. So here for very simple molecule, lithium hydride. So it's it works very well, actually. So, but still, this is one of the approaches where we see the scaling behavior could be better. So we hope that with future architectures of chip, we can find better solutions or solve more complex problems. And the last one I want to talk about is that one. So here we have this design problem that we talked about. And again, it is very useful to imagine you have infinite elements, you have a number of elements connected to each other, and you want to manipulate the angles between the elements such that something is minimized. In our case, it's sound pressure at a specific location. I want to minimize the noise at the driver's seat position. So, and again, this is a problem that's very suitable for mapping it directly on a quantum chip, because we have elements, which are the qubits. We have coupling terms, which is the sound pressure at a given location, so call it badness of sound or whatever you want to call it. And this is the thing that you want to minimize, so you want to find the optimal configuration. And so, and when you think about it, if you just keep one problem in mind, then, so at least I do that, then very often you'll see, this is very different, very similar to the traffic flow optimization. So I always think about the traffic flow optimization because this is the first problem we implemented. And so that helps me a lot to see other problems and find solutions to these. All right. So I think we'll skip these. And so the next things we want to do, so there are still lots of problems we want to solve and haven't solved yet. But just to give you an example, so in quantum machine learning, there are different algorithms. So in one of these is Grover, so a search algorithm for weights again, so we want to get better there. Map neural networks directly on a chip, so in simulation, still we're working on material simulation. High temperature superconductivity, so this is superconductivity at room temperature, so that you don't use this or need these big fridges anymore. That would be very, very useful to have. So it is also very important for some superconducting electric machines. Yeah, and for the optimization, it's always time-critical problems. So when I want to find a solution very quick and it can be formulated as a maximum or minimum problem, then these systems may be useful. So as I said, you won't solve everything with it. They won't replace classical computers. There are lots of things that classical computers can do right now for which you will never need a quantum computer. But so it's worth exploring it and worth learning about these systems because I feel the value or knowledge about these systems, especially as developers, is very crucial in the future. All right. So thanks for your attention.
Come on. Now, what? Yeah. We'll get to that. We'll get to that. Hashtag very funny. At the beginning, I didn't think I'd understand all of that, but I have to tell you, no, it's very good. We have some questions. You don't have to answer number one. You can if you want.
Yeah. So, in fact, there is a problem with that because, so you see, quantum computers can not only be used for the good, they can also be misused for the bad. And you may have heard about quantum cryptography. The thing that, or the problem that we have is that with an optimal or optimally error-corrected universal quantum computer, it would be possible to find the prime factors of any number very fast. So, and you know, RSA encryption is based on that. So, and any encryption that's based on prime factors, so you will be able, not maybe in 3 years, not in 4 years, but at some point you will be able to crack these algorithms like that. So, and this is a problem also for blockchain, because very often we think, well, because it's distributed and trusted, it's secure, but so quantum computers may be a threat for any communication, so that's in that case. But for now, HODL.
I'm going to answer the third question, may I? When I fix a bug in one part of my code, it affects other parts of the code. Yes. Yes, you are. The cryptography question, yeah, the cryptography thing was in the, okay. That's sort of it. Can you get that question back, Stefan? Okay, look at this anonymous one here. How will quantum affect the sector of cryptography?
Which one? Sorry.
Forget it. How will quantum computing affect the sector of cryptography in a user level, on our level?
Yeah. So what you can do with quantum cryptography is establish another communication channel. So you have still a classical communication channel where you exchange information, but what you can do is create a key and communicate over a quantum channel. And so we'll not go into the details because I need a black or a whiteboard for this. But so what happens is that you are able to understand when someone listens to your communication. So the creation of the key can be made secure. So, and if I know that someone is listening, I just don't use that key, create a new one. So that's something that's useful, but still it's not securing communication channels. I will just know when someone is listening, which is already very valuable, don't get me wrong, yeah?
That sort of speaks to the second question as well, doesn't it?
Mm-hmm. So it's possible to use distribution without.
Okay, now I want to answer the third one as well. Mm-hmm. Before we answer the third one, right? Because it's an important question. Who knows the answer to the universe and everything, the meaning of life? Who knows the answer? Right. Now keep your hand up if you know where it comes from. Thank you very much. Somebody yesterday said to me, from Siri. I'm 46, I'm English. I listened to the original broadcast on the BBC. Yeah. Now you come. Okay, I have a question for you, Florian. Why is VW doing it? What's in it for them?
So right now, so it is true, it's more exploring, but sometimes we find problems where we already benefit today. So like this traffic flow optimization, we know that we can't solve or find a better solution in shorter time with classical algorithms right now. And I would be happy if someone disproves us, because in the end, we end up with a better algorithm, it doesn't matter. So, but for materials science or materials simulation, we learn now what these systems can do, and our algorithms, anything we develop generalizes to bigger systems. So once the hardware gets bigger, we have the solution to bigger problems too. It's not.
So does the quantum computing that you're talking about and analyzing and researching have then kind of non-quantum effects on how the other research is going?
Yeah.
Yeah. Okay. That was a long-winded question, but right. Any good ones up here? Yeah, I'd like this one from Chanky Biswas. Will a lot of existing technologies go for a toss, Geflöten, when quantum computing becomes accessible? I mean, what's going to disappear?
So I don't know what's going to disappear. So definitely classical computers are here to stay. So there is no need to replace a classical computer with a quantum computer when it can solve a problem optimally. So, but what I think is that not a lot of things will go for a toss. I've never heard this phrase before, but so that but a lot of new things will come. So we will find solutions to problems and access problem categories, complexity classes that's impossible today. So, and even when you try to imagine what's possible, it's not possible. So very often we talk to to my colleagues at the university, or we talk to hardware vendors and ask, what do you think is possible? And they say, well, I don't know. You have to figure it out. So, and we're trying to.
I would love to answer the next question about entanglement, but we have 6 minutes. I think it'd take about 3 semesters to answer it. I mean, how does entanglement even work? I mean, I'm not even going to let you answer. I mean,
I can't answer that.
You can?
No, well, I can as far as we understood it, but not everything is understood. So
you like that? But the question here, this is a good one from Mr. or Miss Anonymous there. Where can we read about this? Where can we learn about this?
Yeah. So of course, you can say you can Google it, but so what I would recommend is maybe I would expect sooner than later some online courses in quantum computing. So I know that there are some from MIT, so it's definitely worth to have a look at that. And it's not required that you study quantum physics. So very often it's presented as an abstruse and very complex field, and it's not too simple, that's right. But so quantum computing is just a part of quantum physics. So you can learn a lot about it online. So so if you Google, there's one person called Dave Bacon, and so he works at Google right now, and he prepared excellent lecture slides for a lecture that he unfortunately does not give anymore. But you can still find the lecture online, and I once talked to him about that and asked him about a specific problem, and he said anytime he doesn't know something, he just Googles for it, and then the recommendation is his lecture slides, and then he says, well, I don't know that guy doesn't know the solution. But so still, you'll find that, Dave Bacon, so it's very good.
So there's a good one here, another anonymous. You're also anonymous, you're so shy. Okay, it sounds silly, but what are the most, if I was talking to my mother now and she said, yeah, you promised this years ago, what are the most sci-fi applications? I'm skipping ahead a bit here, but what are the most sci-fi applications of quantum computing that are imaginable? And I'll just add a second question so you know, will everybody in this room be working with quantum computing in 10, 15 years from now?
Yeah, I would expect that a big part of this group will work with it because, so it still requires software engineers to write code. So it's not that we have the chips and then you just connect some data, so you need software for it. And usually we access these systems right now with APIs, so we use Python a lot. But Microsoft, for example, is working on a quantum computing specific programming language, so we expect something to come out there as well. So this is something we all would want to have. So there's a lot to learn for software engineers, but we'll not run out of work, and I guess most of you will at some point access these systems.
Because there was a question further down, so it sounds very academic, are there effects on developers' work today? Well, it all starts academic, doesn't it? Yeah. Yeah, it has to, so come on. You have to learn more. Okay, I'm just skipping ahead here, because I'm rude. Feasible for consumer use, etc., etc. What I really like to know, this is the developer conference, and we've heard a lot of information today. We've got another talk after this in 15 minutes, but it's really what is the one takeaway for the guys in the room here, who are developers, who are active today, a very, very interested crowd, have listened for half an hour. Mm-hmm. What's the one takeaway with them? What would you do if you were sitting in the crowd now?
Look up David Bacon's lecture slides. And then the next thing, so it's very important to understand that it's underhyped right now. So because again, it's a very often presented as a complex and abstruse field, but it will change a lot in information technology. So many things that we can solve today will be solved or possible to solve with these machines. And here it says, it sounds very academic. Yeah, there are effects on developers' work today, so if you work on time-critical optimization problems, you can achieve an advantage. So the sooner you learn about it, the more knowledge you build up, the better you will be. So, and anytime it's just important to implement one problem. And there are simulators out there, so I would recommend that. D-Wave provide quantum simulators, Google provide quantum simulators. So use these simulators, they're small. D-Waves is 128 qubits. And for universal chips, or universal chip simulators, it's still smaller because it's too complex to simulate the behavior exactly. But use these simulators to try out what these chips are capable of. And if you can map problems to the simulators, you can also work with real chips. So I would also do that. Okay, let's get one more in, running out of time. What about Manuel's question there? Yeah, about OOP. Do you think we can? I know nothing about that. So we throw away every current knowledge for a career in this field? I don't think so. So object-oriented programming will never go away, so why would it? It's evolutionary, isn't it? I mean, it's incremental. Yeah, and so quantum chips are only used for certain parts of your problem. So it is so very often you will see quantum-assisted algorithms. So you take one part of your algorithms that's slow or can't be solved at all with a classical machine, and this you map to the system. And so it's a coprocessor, and you get the solution out of it, so you will still develop software as you do it now, but you will use an additional API. And it's very valuable to understand these quantum effects, because this is what you really want to exploit. So the superposition, entanglement, and tunneling. So this gives you just additional methods to solve problems. So,
are you at the booth here?
At the booth?
At the booth. Is there a VW? Are you around today?
Yeah.
Yeah?
I'm around today, yeah.
He's around. Ask this guy lots of questions. We're going to wrap it up now. We carry on in 15 minutes, but please give a very warm thank you to Florian Neukart. That was amazing.
Thank you. Very good.
Back in 15 minutes.